I'm going to do a little workshop with you guys. I'm going to give you a big fat present, because you all stuck around to the end. The other people will also get the present, but you get it today. What I'm going to give you is a flexible twin, but before we start, the very first thing to clarify, super important to me, is this is not another buzzword. I had to come up with a good title, so apologies for that. I'm actually going to deliver something today. So a couple of years ago, I was walking through London at night, and I saw an advertising from not PwC. I'm sure there are PwC people today here, but from a quite close competitor. And their advertising said that tomorrow doesn't happen overnight. And I thought, wait a minute, tomorrow literally happens overnight. Like, what are you talking about? Or let's play a little game. I found a flyer in one of my former offices, and the question is, did I write this flyer? Did ChatGPT write this flyer? Or is this real? So the slogan of this company is personal mobility for the digital generation. And this company is saying we are a scalable, legislation and demographic-driven tech startup with unique enabling automotive suspension IP that helps allow the lowest CO2, NOx, and PM emissions fully enclosed, fully powered road vehicle for any given power source. Isn't that amazing? And even at the time when I saw that flyer, I had to mark these little places there, because it's like, how much more bullshit can you have? This is 2014, and I think they had an early version of ChatGPT or something. Like, how can you come up with something like that? And to this day, I don't know what they're doing. Do they sell the suspension? Do they sell the IP? Do they sell the car? It's complete crazy. So today is not going to be this kind of stuff. Today, I'm going to give you a little present. I'm going to give you a basic model that you can use for like 90%, I would say, of all manufacturing problems that you're facing. I just checked the program from today, and there's a really big chunk of manufacturing studies going on with AnyLogic. So it's a big, big part. But what you're going to see, and I'm trying to convince you of that, is it's not only for manufacturing. This model will be useful for healthcare studies as well, for hospitals, for restaurant businesses and these kind of things. So we can brainstorm later on what else it could be used for. But it's a very broad thing. And it's not just the model. You're going to get the best practices of how do you really build good models. It all sits on top of the kind of workshops I've done over the last couple of years and a lot of learning over the last couple of years of how do you build really, really good models. And if that's not enough for you, you can also get hands. If you're not interested in this model, I have lots of little hands, and we'll see later why. I just don't randomly carry hands around. So who is this guy with the hands? Done a lot of AnyLogic modeling, but it's a little bit boring. Let's not talk about that. Let's talk about my models. The coolest model I've built was last year for Tesla, where I could recreate the Giga Berlin factory. And it was not cool because we could work for Tesla. It was fantastic. But we did some really cutting-edge stuff there with AnyLogic. So that was really, really great. And will be presented at the German AnyLogic user meeting in a month's time. So stick around for that. The largest model I ever built was for Rolls-Royce. That was together with Decision Lab about 10 years ago. And it was ridiculously big, but really, really cool. Then there's the most beautiful model I ever built. That was for New York ferries, where I figured out that you can actually include Google Maps 3D imagery into AnyLogic models. So I could have the nice New York skyline. Beautiful. But obviously, I'm also a consultant, so I can't just talk about beauty and all that stuff. The most impactful model I've ever built was for an aluminum plant in Switzerland, where we could measure the impact of the model very precisely, which is rare, really, really rare. And it went into the millions, so this was a really, really good thing. So that's enough about me. Let's start to dig into a manufacturing flexible twin. First of all, let's talk about why, and let's talk about the pain that we all share. We've all been there. Being a simulation modeler is not always fun. There's a lot of pain. And the first dimension of pain that I want to talk about is the most cheerful one, death. We'll talk about models dying. It's a very sad thing. It's very hard for everybody. So I thought, okay, I'll go to ChatGPT. I'll ask ChatGPT, can you help me make this explained to people in a kind of cheerful way? And ChatGPT was really not helpful at all, but in a funny way, because it literally said, use playful metaphors, like simulation models are the drama queens of the tech world. I thought, yeah, it's kind of passive-aggressive, but yeah, okay. As a second step, it suggested to playfully explore the stages of grief that simulation modelers go through when a model dies. So we'll do that. Stage number 1, denial. No, the model's still working, all is fine. Stage number 2, anger. Like, the fuck is that not working? Stage number 3 is bargaining. It's like, oh, maybe if we just take out this one part that isn't working anymore, everything else will be fine. Stage number 4 is depression. We are effed. And stage number 5 is acceptance. We're effed, but let's start from scratch. So then ChatGPT suggests to end with a funny and optimistic message about the resilience of simulation models, like simulation models may die, but their spirit lives on in the laughter and lessons they leave behind. So no, let's not go there. The real reasons why simulation models are dying are manifold. It's typically things like reality changes, your business changes, model operators change. But what do you think is, in my experience, the biggest reason why simulation models just die? Any idea? Just shout it out. Obsolescence, yeah? Any others? Scope creep. Oh my God, you're scaring me. Oh, we get the cheese. Yes, that is, in my experience, the biggest one why a model dies is the management changes. And they're like, well, you don't trust the model. Okay, we build a new one, whatever. So, death is a very awful thing, and we feel the pain. Another pain we all feel is that our models often do not scale. You might have a beautiful model for a machine. Let's see if that works. Yeah, beautiful little machine model, which is fantastic. If you build it right, it might even scale to an entire factory. That's also very good. But does the entire factory then scale to your entire company with lots of factories all over the place? And if it's doing that, does it then scale to your competitive landscape or legislation or climate change or whatever else? Scale is typically quite a problem, and models often cause us pain because they don't scale and things are changing. That's not to say that your models need to scale. In my previous workshops, I always say your model needs to have a purpose and you stick with that purpose. But if your model purpose is to be flexible, and that with digital twin world, that very often is the purpose these days, then this is a pain that we're having. And then there's just change. We already talked about it. Change causes us a lot of pain. And the reason why I put up Berlin as the background image for this presentation is Berlin is really, for me, the epitome of change, and my home city. The kind of change the city has gone through the last 100 years is crazy. If we have a look at this image here, do you guys know what this is? Again, just shout. Sorry? It's a map of Berlin. It's an image from space at night of Berlin. Sorry? You see that, right? You've seen that online. But it's actually true. I'm not sure if you can see it on these screens. I hope you can see it. But there's a distinct difference between the light on the right-hand side and the light on the left-hand side. Thanks for making it darker. Because West Berlin has different lights than East Berlin, but this is a recent image. You can still see the wall of Berlin from space and the separation. So, things are changing, but not always. And your models need to be able to also include not changing, or changing at a very, very different pace. So we have lots of change, new requirements, situations change, your requirements change, all that stuff. Now, this workshop is a little different to previous workshops. Previously, I always made a really strong effort to include everybody. I had lessons for beginners, intermediate users, and super advanced users, tried to bring everybody along. With the present that I'm going to give you today, it's slightly different, but still everybody can benefit from it. But let me put this present into some context. I identified 5 aha moments that every AnyLogic developer goes through. Let's see where you guys are. The first aha moment is that you realize I can drag and drop stuff, click play, and things are happening. Who's at that stage? Or who's been at that stage? Couple of arms. Second stage, let's see who's there, is, well, I can actually push custom agents through these blocks and make it a lot more powerful. Who's at that point? There we are. Next stage is that you realize, well, with these agents, I can actually replace all these flowchart blocks. I can create pure agent-based models. Who's been there? Now, the fourth stage is that you realize that these flowcharts blocks are actually really, really useful. And you go back, say, no, 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 I actually want to keep them. I don't need to reinvent the wheel. But if I combine them, agent-based and flowcharts in an elegant way, I have infinite power. There's literally this aha moment where you realize I could now model any logic with any logic. I can model anything. But there's a fifth stage. You think you have infinite power, but then at the fifth stage you realize, well, if I leverage object-oriented principles and good Java coding, I can actually do my infinite powers in an efficient way and in a way that things scale, are elegant, reproducible, and all that good stuff. And the present of today basically falls into the right two aha moments. But if you're still in the first three, that's also fine. I'll point out the learning lessons to you. But if it's too advanced, it's fine. You come to me afterwards, and at least you get a hand. We'll still talk about why the hell do I have hands in my pocket. So we now understand the pain that we are all sharing. Let's talk about the solution that I offer, which is this base model that you can take for 90% of manufacturing problems, and they will scale and will be elegant. Let's first talk about manufacturing a little bit, because some of you are from completely different backgrounds. In manufacturing, we have a factory. What does a factory do? Shout. Just a little louder? It makes stuff. Fantastic. It makes stuff like this. There's a factory in the world that is producing hands. If it doesn't make hands, it may create useful products like beautiful little hats. Come to that as well. So factory produces stuff. What does it need to produce stuff? Ingredients. Yeah, we'll come to those. Machines. So in your factory and in our base model, we will have machines. And these machines can be super different in reality, right? This machine is actually an interesting concept. At McKinsey, when I was working with them, they have this model factory in a box. In order to teach CEOs who are very stubborn at learning and don't want to change, they literally pack up a little factory in boxes, take it to the C-suite, unpack it, build up little machines, and the CEOs and CFOs and stuff, they have to squeeze juice in that little factory and learn about throughput and all that stuff. So there are these kind of toy machines. There are really big machines. That's like some truck in the Ant Mountains in that gold mine. There's me next to the coolest machine I've ever been next to, which is Apollo 11 in Washington. This machine is pulling cable cars through San Francisco. This is a pizza machine. This is literally a vending machine for pizzas. There's no human intervention anymore. Or the largest vending machine in the world. Lots of different machines. But what they're all doing is they try to improve something. So if you have a little product like this head, the machine might add another feather to it. So you as a product go through the machine, something is done on you, and you are being improved. The other thing in manufacturing, you guys already mentioned, you produce products. That's the whole point of a factory. And the kind of products that you produce can be super, super creepy products. I'm really sorry about this, but this is how you make these puppets. They're super innovative products, like bacon bandages. I was hoping to get bacon bandages to you today. But unlike the gentleman from Amazon in the first talk who had a really good experience with Amazon, I had a bad experience with Amazon and no bacon bandages today for you. But hands. Obviously, there are products like hands, which you can do fun little things with, or these hats are actually made for chickens. So if you have chickens and you want to put a hat on them, you go. So you can create all sorts of products. But if you are a product going through a factory, somebody already threw in the word of stuff, you need materials to produce your products, but you need something else. Any idea? The product needs something else. The product needs to know its recipe. Where do I need to go? Which machines do I need to visit? What do I need to consume where? How long do I need to stay at that machine? I call that a recipe. There are lots of different words for it. So recipe is like a very intuitive concept, but still I have to read to you the worst recipe in the world. And this is real. This is hakal, which is a food in Iceland. Anybody ever had hakal? And neither have I. Step number 1 for your recipe is you go to Iceland. Step number 2 is you catch a Greenland shark, which is known, this is not ChatGPT, this is real, which is known for its toxic flesh due to high levels of urea and other chemicals. Mwah. Step number 3, you take the shark meat and you bury it in the sand on the beach to let it rot for several weeks. Step number 4, after the rotting period, you exhume the meat and hang it dry in a smoking chamber for several months so a brown crust forms on the exterior of the meat. Apparently, this tastes absolutely awful. So a recipe is a very clear instruction how to make something. You visit the sand, you spend some time there, then you go to the smoking chamber, you consume a little bit of materials or ingredients like smoke or whatever, and then you're done. So we'll have this kind of concept as well. There are lots of other fun recipes like for 80s foods, fantastic. And then the last thing your factory needs are raw materials, inventories. Your products, in order to be produced, need stuff, like feathers or smoke or any other thing. So in our base model, we'll have inventories, 2 different types of inventories for this one. We'll have like factory-wide inventories that span the entire factory. Everybody has access to those, kind of big. And then kind of machine-specific inventories. If you are the operator of a machine, very often you just have a tiny little inventory and you just pluck your feathers and put them on the beautiful hats. So we'll have those as well. Now, inventories obviously are super dangerous and can cause all sorts of problems, but we have to be careful. So things can go wrong. You've probably seen this video, but what I really like is not this guy. Everything is broken now, and then he comes. And now he wants to save things. It's fantastic. So we'll have these dimensions in our manufacturing world: machines, products, recipes, and inventories. And what you're going to get is a very generic model design. I'm going to take you through this generic model design with reusable assets, with very strong architectural foundations. Some of the stuff I'm not going to go into the details because it's literally what I preached last year and the year before. So it's really building on those foundations. And it is a very future-proof design, and you'll see why when we talk about it. So let's start digging into the actual model. Let's first understand the hierarchy of things. And you guys know that typically the top of the model hierarchy is our good old main. We'll see that as well. Embedded in main, we'll have an agent type called factory, so we can have one or several factories on our model. Embedded in factory will be one or several machines and one or several inventories, which are factory-wide inventories. And then we also have machine-specific inventories if we want to. We'll have the good old products, which are flowing from machine to machine to machine, looking up their recipe and doing the stuff they're supposed to do. And if they need to consume some material, we'll also have a material request agent embedded into this. Just to paint the rough hierarchy picture before we dive in. There's a whole other side to this model, again, preaching what I taught the last couple of years, which is completely separating any animation from the logic side on the right-hand side. I'm not going to go into too much detail, but this is my present to you as well. You get a little starting point for easy, flexible animation. At the moment, it's kind of basic, but you can do with it whatever you like. So you can make it as fantastic as you want. Alrighty, so time to dig in then and talk about our little model. Let me close this one here. Now, first of all, can you all guys see that? Otherwise, I would recommend you come a little bit closer so you can really see the code on the screen. And for those in front, is it big enough? No. Not too big? Not big enough? I can change the resolution. See if that works. all in German. All right, let's try this one. Is this better? Lots of yes, good. All right, so here's a lesson also for the beginners. If you're in the first 3 aha stages still, good lesson to learn. How on earth do you try to understand an existing AnyLogic model? It is a bit of a skill, it is a bit of an art, but I'll teach you a couple of heuristics now, because this is a model you don't know about. But in your career, you often come across even your old models from 2 weeks ago when you have no idea what the hell was that. So trying to understand a new model is a really good skill. The first thing you need to do is understand the hierarchy. I already kind of plotted it to you, but let's explore it from the model side. You typically start at main, which is always typically the highest level of the hierarchy, and you try to figure out what is embedded in my main. What kind of agent populations do I have? And in our case, we have 2 little things here. We have a population of factories, which is an empty population, really good practice, see the older talks, and a population of factory animations. This is the kind of left-hand side of the structure of the UI side. We won't go there. So we figured out the very first stage of our hierarchy. Let's go back to the hierarchy. We figured out this bit here at the very top. Factory is embedded in main. The next step you should be doing is try to understand main itself. It's characterized by parameters. So we have a couple of parameters that define main in this case, the number of machines per factory, machine duration. We'll come to these things in a little bit. And the last thing to understand for main is what happens is when it's initialized. And you check that in the on-startup code, where I follow good practices and always use an initialization function which groups everything together. So I can easily go into my f-init and see, when main is created, it creates one single factory with this f-create function, which literally adds a factory to the population of factories and passes on these parameters. So in your quest to understand the model, let's keep doing this. We went 1 level into the hierarchy, so let's explore this factory now. And we do now exactly the same steps. We figure out what's embedded in factory. Embedded seems to be an empty population of machines, empty population of products, and empty population of inventories. So we understand the second level of the hierarchy now. The factory itself, second step, is characterized by these parameters. So factory seems to be defined by these characteristics. And then the third step is, again, there's an f-init, what happens on startup. And in this factory, when a factory is created, all it's doing is creating a number of machines, which is parameter-driven, and creating several inventories. So let's start with the machines. We are instantiating machines as many as defined by this parameter, and we also give it a little probability if that machine has an inventory. At the moment, this is random. In your models, you'll fix this and link it up to some data. So we'll do the same steps now. We are instantiating a machine. Okay, so what happens in a machine? A machine has itself an empty population of inventories. So we are at this stage here. How is a machine characterized? There's just one parameter, if it has an inventory or not. And how is it initialized? That is this f-init function, and all it's doing is calling a little set inventory, which instantiates an inventory agent at this machine if the parameter tells you to. It's a bit of more advanced code, which we'll come to in a second. So we've explored machine and inventory now. Let's go 1 step back up into the factory, because we skipped on the inventory bit. The factory also creates inventories by just adding things to this population. And the inventory itself, let's explore that, following our good old heuristic, has nothing embedded. So we've finally reached the end of the hierarchy tree now. Fantastic, good insight. How is it characterized? It has a parameter initial quantities, which is what the inventory will have at the start of the model. And is there an f-init function? There is, beautiful. So let's check out what this one is doing. And this one takes this initial quantity parameter and with a bit of Java code copies it over into a collection. Now here's a little lesson for kind of intermediate users, not super beginners. But if you define an agent with a parameter and that parameter is something like quantities or something that will actually change during the life of this agent, if you're an inventory, your quantities will change all the time, then don't make the mistake of using this parameter as the actual value for that inventory. Instead, copy it over at the start of the agent, like we are doing here, into a separate object, in this case, this collection, and this is where you do those changes. The parameter is just to characterize what it is at the start. Alrighty, so we go a little bit deeper now. We are reaching stage 4 and 5 of the aha moments now. Our little collection of storages is a linked hash map, which is a good Java construct, but I'm not going to go into the details of what it actually is. But essentially, it stores for us how much material, quantity, do I have of a certain material. And you can see there are these weird things here now, right? POJO material and JC quantity. So in our quest to explore this model now, which we don't know, this would now be a good state to check those out. These are Java classes, really, really powerful and useful to use for your models. Don't skip on your Java. And this POJO material, I use the POJO, which stands for plain old Java object, as a prefix to remind myself this is a so-called immutable class, which essentially means if I have a POJO material object, it's defined by a name, for example, feather. It is of a certain type, which is defined in an enumeration, so it could be a raw material or something processed or whatever. This is up to you. You can change this. And it's measured in some kind of unit. So feather, I would probably measure in grams. Now, immutable means that as soon as I define one POJO material object, and I follow a couple of steps, which I describe in the little help up there, a feather object that is measured in grams and is a raw material will never be confused with another feather object that is measured in grams and is raw material. Java, with all the dot equals and equal panes that we always talk about, will see them as equal, and you can never mess it up. So the concept of immutability is really powerful when you want to define some concepts like materials. And then we had this value element class where we say how much of this material do we actually store in our inventory. So let's explore this JC quantity, Java class. I use that prefix to remind myself this is the Java class. This is mutable, i.e. I can change this all the time. A quantity object I want to change all the time. It represents a quantity. And I'm defining it in a very simple way. It's just a double number of how much, and then a second field of how, what unit. So a JC quantity object of 100 metric tons would be just that. But because it's mutable, I'm giving you really, really useful little functions here in the Java code to add something to this 100 tons of something. You can add 5 more tons if you want to. And this code will just basically make sure with lots of sanity checks that the units match up. So if you want to add 5 grams of feathers to 10 kilograms of feathers, you can do that with unit conversion. But if you want to add 5 liters of water to, I don't know, 10 screws, that is something that should throw an error. And you can manage that with these Java classes quite elegantly. Same with removing quantities, which are just public functions. They make sure that if you want to remove from 5 kilograms of coal, if you want to remove 10 kilograms, it's not going to be possible. It will just remove 5 and tell you about it that there's not enough stuff. And this code is for you to extend. You can do more sanity checks, you can do unit conversion, all this kind of stuff. But it's a really good, solid setup. Now, our inventory has this initial inventory, like how much feathers do I have, how much sand do I have, whatever. We'll define that. And then we have these little public functions here as well to add materials to it, remove materials from the inventory, check if we have something. That's all there for you, and you can just use that. Now, one thing we haven't yet discovered are the products. Here is again a lesson for the first 3 AHA stages of exploring your model. We've now fully explored the static side of the model, the hierarchy, the definition of the agents, how they're kind of sitting together, and how they're instantiated at the start, but we haven't explored the dynamics of the model. And this is a bit more difficult, because you need to look for a couple of key objects in your model. Any idea what you need to look for to explore dynamics of the model? Experiments? Any other things that show you, oh, something will happen here at runtime? Events, very good, yeah. So events is something to look for. I know where there is one event, and that's in the inventory, actually. So at runtime, when we have an inventory, this will restock itself. Using a replenishment period, it will just randomly, from time to time, restock itself with a bit of random material, which in reality, obviously, you need to change this code and link it up to your real replenishment algorithms. So look for events. Look for dynamic events as well. That's a bit more intricate, but also really important. And then there's one other key object that you need to look for to understand dynamics, and that is the source block, because that is actually creating agents at runtime. And we have one source block in our factory, and this source block is creating product agents with a specific arrival rate. So I'm just using a parameter for that. Typically, you would also do this in a data-driven way. When do my products actually arrive at the factory and want to start their product journey? So we create these products. These new products that the source creates are added to a custom population pop products. Really, really good, useful tip. Always do that. Use an empty population of products, and in your source, add them to this population, because now your factory has easy access to all your products. You can just loop through that population, and you have it in your hands, and you're in control. So let's look at product. We haven't looked at the product yet. We follow the same heuristic. It has something embedded, a material request agent. We'll come to that. It seems to have a flowchart as well, so something will happen at runtime, and it's defined by a recipe, which is a linked list, another Java concept. Get up on your Java, it's super powerful. It's a linked list of POJOs again, this time a POJO recipe entry. So there's another little Java class here that defines a recipe entry. So for Hakal, the first recipe entry would be machine would be the sand, the duration would be 3 to 6 months, and the materials to consume would be nothing. You just need to rot. That would be your first recipe entry. The second recipe entry for Hakal would be the machine would be the smoking chamber, the duration would be 3 weeks, and the materials to consume, which is a map of material and quantity again, just like an inventory, would be some amount of smoke in this example. So when we instantiate our products, we give them a linked list of these recipe entries. So the product will know, first I need to go to this recipe entry, then to this, and I keep on going. And this is a really powerful base concept to follow. Now, your products are being created in the factory. They arrive, they get their recipe, and the first thing that they're doing then, and this is again learning for how to explore a model, is now you follow the flowchart. What do the agents actually do? The first thing that they're doing is they're starting their next little step with a little bit of sanity checking here. Another tip for aha moments 3 and 4, I would say, is sanity check the hell out of your models. Write as many sanity checks as you always can. Just make sure that things aren't broken at a specific stage. So in our little case here, the product will start the next step. And all that is doing is it takes the to-do steps, which is the initial recipe. So I have my list of things I need to do. And it basically removes the very first step and turns that into the V current step. So the product knows about its current step. What do I need to do right now? This is all that's happening here in this little block. And then we use this elegant concept of mixing flowcharts with agent-based. Stage 4, infinite power. We don't have to draw really complex flowcharts. There's this simple flowchart here, and now we're sending our agents into their current steps, machines, arrival block. So in the machine agent, we skipped over it when we explored the hierarchy, but the machines have their own little flowchart here with a little entry block that is waiting for products. So you as a product, with your recipe, you now look, okay, first entry, sand. I'll go to sand. I arrive at the sand machine, and the first thing I'm checking is, do I need some materials here? I have that in my recipe. I check my recipe, do I need some materials? At this first stage, I don't. I just need to be there for a certain amount of time, so I'm going this lower flowchart here, and all I'm doing then is to spend a little bit of time in this delay block, in this machine. I look at my recipe again, and I get the duration. How long do I have to rot? Which is 3 to 6 months. So I'll rot for that amount of time. Notice that the capacity here is 1. We'll talk about that later. You can change that. And then you tick off your recipe entry, which literally is just removing that vCurrent step from the product. So you're like, I'm done with this step now. You check, do I have another step? You look at your recipe. Is there something else for me to do now? This has next step is literally just checking, is there more steps to do for me? And another tip for aha moments 4 and 5 is check, you see that I'm using these public functions, like has next step. I could easily just write call steps to do dot size larger than 0, but what I'm actually doing is I'm using a little function here that returns a Boolean value, which is doing the same thing, but it is more encapsulated and will help you in the future to scale your models. So in our case, we do have another step. So all we're doing is we are starting that next step. We call start next step again and do this elegant thing again. We just jump to the next machine of our next entry. So we are jumping to the smoking chamber now. We arrive at the smoking chamber and follow the same flowchart again. We check, at the smoking chamber, do I need materials? And yes, this time I will need materials. I need some smoke. So now we're following this other branch here where we actually request those materials. And here we're using a neat little trick, maybe a hard stages 4. Me as a product, I request these materials. We'll come to that in a second. And then I put myself into a dead end, a wait block. A wait block, the definition of is that I come into it and I'll never get out of it again unless something very special happens. But by default, I'm stuck here forever. So I'm stuck here forever as a product, but I just created my material requests previously. And in my material request, what I'm doing is I actually instantiate new little agents in myself, in the product. Material request agents are embedded in the product. So I instantiate those with the material that I need, with the required quantity that I need, at the machine that I needed, and the material request knows what it's supposed to do. So let's look at the material request agent, follow the same heuristic that we always do. It's defined by 4 things. What material do you need? How much do you need? At which machine do you need it? And something else. We'll come to that in a second. But the little trick here is that we don't just instantiate those material request agents. We also put them into a little flowchart within the product. So we're like inception level now. The product is stuck in the machine flowchart, in the wait block, and we're using the same little spiel now for making our material request agents getting stuck in a wait block until something happens. So they will never get out of it, these material request agents, until something happens. And what needs to happen is that they need to try to satisfy these material requests now. They have a certain quantity that they need to figure out to find from inventories. And this is what I'm using a state chart for. And we'll come to how you can extend that in a minute. The first thing that they're doing is they check, am I actually at a machine that has an inventory? So if that's the case, and I'm a machine that puts little feathers on it, do I have a little feather inventory? I just grab my feather from that. And if you have that, you will try to source the materials from that inventory, from your little local machine inventory. And the sourcing is using the remove quantity public functions, the add quantity public functions. It's checking, is there enough stuff for me? If I need 5 feathers and my local inventory only has 4, I will grab those 4 feathers, but I'm still 1 short. But if all 5 feathers are there, I'm going to grab all 5 feathers. If not everything is source, you're still missing a feather, then you're going to go and try it in a random factory-wide inventory. So in this case, we're just choosing a random factory. Again, this is where you would come in and make this refined. And we try the same thing again. We source from that inventory and try to get our stuff into place. And with the state chart, we can very elegantly try this and again every couple of minutes. It's parameterized, so you keep on trying until you get your bloody feathers together. And until you don't get them together, your product is stuck. Your material agent is stuck, your product is stuck, and you won't advance. But at some point, you are done. The material request is successful. We've got all the feathers, fantastic. And now we're using this little trick of the 4th parameter. Where are we actually waiting in which wait block? And what we're doing is we call the .free function in this wait block. So the material request agent that was stuck in the wait block is now pulling itself out, is bootstrapping itself out of the dirt, freeing itself. It's very happy, and it can continue in the little flowchart. And what it's doing before it kills itself in this little sync object here is one last thing. It checks, are there other material request agents that are still stuck in the wait for material request? Because if they are all done, if nobody else is waiting, we've got all the materials that we need, we go one level higher in our inception and now tell the machine, hey, dear product, you were stuck in the wait object forever. You can now free yourself. You can bootstrap yourself out of this. Everything is satisfied, and the product can now continue and do its machining. And this is not trivial to understand. I don't imagine you can follow this right away unless you're step 4 or 5, then it's probably fairly trivial, but it's very elegant, very, very elegant way of managing this stuff. All right, so we are at step 3 of our recipe. We have found the smoke. We've been smoking for a couple of weeks, and we formed the tasty brown crust. We check if there is something else to do in our recipe. This time, there's nothing else to do. So we use the other branch now, which takes us basically out of the factory. So we're using this kind of final flowchart here for some KPIs if we want to. But essentially, this product is now done. It can leave the factory, and we're finished. And this is how you explore a model. We've done this together now. There's not much more to it. So some of you will probably think, oh my God, what the hell is he talking about? That's fine. Some of you will think, come on, that's trivial, Ben. But that's also fine. We need to hit the sweet spot in the middle. And this is the basic model. Now let's actually look at it. It's kind of mean that I didn't show you the model before, right? But I did it on purpose. I didn't want you to get distracted too much with the animation, because the animation, remember, is a completely different branch of this model. But with the animation that I'm kind of providing you in a very simple way is you get this little 3D window of your factory. We are randomly placing machines in XY coordinates. Obviously, that's also just a starting point for you. Some machines have little inventories next to them, and we have these kind of factory-wide inventories, which are a lot larger. And if you fast forward a little bit, you can see how the products consume materials over time, but also how the inventories restock themselves. So there's not a lot of magic going on there. Just to get you started on this UI thing, if you want to improve and make it look better, the UI sits on main. We talked about it briefly at the start. Empty population of factory animations. All we're doing is we create one factory animation for a given factory. And this concept of agents being used to animate other agents I presented at a previous workshop, and it's extremely powerful and efficient computationally because you have full control over your animation. But this factory animation at the start creates machine animations, UI machine agents, and just puts them into random positions. Same for the inventories. So here you could easily put them into better positions. Alrighty. Now this was a tour de force, I know. What do you actually do with this now? How the hell is this going to be helpful? Well, first of all, I'm going to give you the link. It sits on the AnyLogic cloud. You can just download the source files. Step number 1 is you rewatch this video. I have had a couple of people who are saying, Ben, we're so thankful for the workshops. I've watched this one at least 10 times and click pause, play, pause, play, pause, play. And you probably have to do this with this as well. It's very dense and very packed. So do that. Get to understand the model. Let's explore how you can take this forward for your 90% of manufacturing applications. With this structure, once you understand it, it's very easy to extend. So you can easily say, hey, my machines in my manufacturing, they're not these simple machines. They have operators. They need people to work on those machines. So you can easily parameterize that now, give it a Boolean parameter has operator, and then an integer parameter number of operators, and you replace the little delay block with a service block and a resource pool. Then you would have operators that are bound to individual machines. But you can also have factory-wide resource pools. You just put your resource pool into this factory and make it parameter-driven as well, and have your machines pull from your factory's resource pool. All possible. And if you're at stage 4, it should be very easy. You can extend your recipes. You know, the recipes that we talked about for Hakal, they were kind of trivial, but you can easily include more information. For example, not just visiting machines, but visiting inventories as well. You add another field to it of an inventory that you want to visit, or a cool-down period. I need to go to this special area and just cool down or warm up for a certain period of time. You extend your recipe entry with those informations. You can extend your machines. This machine agent is very basic. It's just a simple flowchart. You can easily copy and paste this agent type and make it extend or inherit from this machine and give it a more detailed flowchart if you want to. But you can also go and use our material handling library and replace your machines with material handling flowcharts. So you can extend logic. You can switch logic and layouts as well. So maybe you didn't notice, but in main, when we create this one factory, we quite intentionally only create one factory, but we can create 100 factories if we want to, and parameterize them. Set them to different locations, make them interact with each other. Maybe one factory sends raw materials to the next factory. So you instantiate more than one factory, and that's literally another line of code in this case. You can change the layout of the machines. At the moment, the model is quite space agnostic. We just put them in random coordinates, but the products actually just jump instantaneously from machine to machine. But in reality, you would first of all place your machine agents at the right coordinates, and then introduce a concept of space. And typically, what that would mean is that instead of having this very simple material request agent, which is literally a piece of paper trying to get some feathers, you could replace this with a transporter from the material handling library. Or you use the material request agent to request or seize a transporter from a transporter fleet that sits in the factory agent and say, hey, I'm a material request, I need a transporter, you need to drive me to my current machine or to the inventory that I need to get to that I decided, just some random factory inventory, let's drive there, and only when we arrive, I can just extend this state chart with the on agent arrival, only when we arrive do I actually pull from this inventory. Again, at stage 4 and 5, this would probably take 5 or 10 minutes. We talked about changing recipes. So what you can also do is increase the level of detail. We talked about transporters for material requests. We can use material handling concepts for some machines or all machines. It depends. Typically, you have some machines that are not that relevant, but you have other machines which are very, very, very detailed. So you can use the material handling processes for that. Same with storage. We've heard some glorious remarks about how good the storage capability is of the material handling library. So in your inventory, instead of using this little linked hash map, you can easily put a little storage block here and use that to store and retrieve your stuff and not rely on this bit of code here. It depends on the purpose of your model. This is super efficient and very, very fast for large-scale things, but if you depend on storage spatiality, then you can easily replace that here as well and just still keep the structure. You can use the fluid library. again, for your storage. Maybe some of them are stored in kegs or in tons or whatever, and you store them using the fluid library and add some other public functions to retrieve fluid from that or inject some more fluid when you're restocking. And then lastly, of course, you need to make this data-driven. And there's a really little simple trick for this model, how to make it data-driven. You literally search for random in the model, in the search function, and you'll get all the randomness in the model, which you need to replace with some data-driven stuff. Search for random and search for uniform. Now then, the holy grail is to take this one level further and enterprise it. Do this enterprise simulation thing in the AnyLogic cloud. And the cool thing with this structure is, that's the very last thing I want to mention. We've seen how you upload models to the cloud. That should be relatively clear. But what you can do now with a structure like this is to say, hey, I want to upload the entire model with all my dozens of factories and hundreds of machines. But I can also say, you know what? I only want to upload a model with one specific machine. And I define the parameters for that one specific machine. So what I'm doing is I'm changing the top-level agent here and saying, please just upload one machine. I don't need to model all the other machines. You can go all out crazy and just upload one machine and define that machine with the parameters that you have and just make this one machine work. If you follow encapsulation and object-oriented principles, your machine will know what to do. It will get orders, it will process them, it will get materials, and do its thing. You just need to define it well in the inputs. So with that, in the cloud, then, you can do all the cool things that you know about. You can parameterize the whole thing, do all these cool parameter variation experiments, Monte Carlo, now optimization as well, and go all out crazy. So next steps then for you is to literally just go to this URL. This is takes you to the cloud. You can download the source files. You can play with the model or use the QR code and go crazy. Now, the first person who will use this for a commercial model, for a real model, or for like an academic model, the first person that's doing that, write me an email and you get a little prize, because that would be really, really cool. I think if you understand this model, it will save you a lot of time. You stand on really, really solid shoulders. You will not run into any dead ends. You can scale and flexibly change your models. That's what I wanted to share. And with that, thanks for listening. Have a great after conference. Happy to take some more questions. I think we do have a little bit of time. But thanks a lot for listening. I hear somebody.
Hello?
Yeah, here.
Yeah, there you go.
Beautiful.
Hi. Thank you so much for the workshop. It was very interesting. I was wondering when you publish on the model manager, you were saying that you can pick the level. So let's say you want to publish only one factory.
Yeah.
If you pick the factory agent, since you have it separate from the UI, so you won't be able to see the animation, right?
In this case, yes. This is
Okay.
how I structure the model right now.
Okay.
So you wouldn't see animation. But
Okay.
you can change the structure of the model and have your factory animation embedded into the factory, and then you could work that out as well. Yeah, but it's a good point.
Okay.
Typically, I often upload models to the cloud just for the performance reasons, so I don't care about the animation. But yeah, you could change that. That's a good point.
Okay. Thank you so much for the present.
Pleasure. Any other questions?
Here's more of a comment. Thanks for the presentation, Ben. Talking about going through the model and trying to figure out that hierarchy, I hope everybody noticed all the comments that you added and all the descriptions to the variables, right? Most of the time you can just read through that and it tells you where to go. So always working with Ben, I never really need to ask him why did he do something or where did he put something, because there's comments everywhere for everything. So I just wanted to highlight that to those, but I think everybody saw it as you were going through the model.
That's a really good point. Thank you, Jakob Ben. That's a tip for aha moment 1, 2, and 3 is bloody document your models and do it in the description tab. It's super, super powerful and useful. It's my absolute second nature to document everything like parameters, especially functions, super important. And done it in previous workshops. I'm happy to repeat it. Don't write what this is doing, because you can see that in the code. Write why this is there. Why should you use this? What is this for? Thanks. Any other questions? All right, thanks a lot for that. I hope it's useful. You'll get a present if you use it.